Here we are working with a weak acid system, which is in equilibrium, and we want to figure out what is the pH of the solution at a given concentration. For this type of problem, you should always try to find two initial values that you have to be given. First one is the acid dissociation constant, which you can usually find in a table for this type of acids. In this case, it's given. And the second value is going to be our initial concentrations. Now, with that, we can build an ice table. Ice table will tell us how concentration changes until it reaches equilibrium. So, my initial concentration, that's the given amount of my reactant. Water, we don't look at it because it's not part of our equilibrium expression. It's a pure liquid. And my products at the initial time, just as I start, the concentration is going to be 0. As time passes, my concentration changes by a certain amount. And all that I know is that for every one molecule of my acid that dissociates, I get one for my hydronium, one for my conjugated base, leaving me with my initial amount minus that certain amount, we're going to call it X, at equilibrium point, and then X for each of my products. We can then plug that into our acid dissociation expression, concentration of my products over concentration of my reactants. And because we're dealing with a weak system, we can assume that the change in X is very small compared to the initial concentration, which is what we did just here. That makes our lives a little bit easier. As you can see, the acid dissociation expression becomes simplified, and then it's just a matter of doing a little bit of algebra, a little bit of rearranging. We move our numbers to one side, our X to the other, and then we just solve for X. Once we have that number, 1.62 times 10 to the minus 5, we substitute whenever we find X. We have hydronium, we're looking for pH, and as you guys know, pH minus the logarithm of hydronium, giving us a value of 4.79. Now, in our next example, we are looking at a similar system, weak acid, dissociating, but we want to figure out not only the pH, but also the percent ionization. Percent ionization is going to be defined as the ratio between my hydronium concentration and my initial amount of acid. Basically, how many protons are you getting from the system, how efficient it is at dissociating, and of course times 100 plus 1 in percentage. So for that, the setup is pretty much the same as in our last example. We have an initial concentration for our reactants, our protonated acids, and then we have nothing for our products. Water, again, doesn't count. Changing concentration, for every one of my acid that I lose, that's why I have a negative sign there, I gain one of each of my products, leaving me with this expression for my equilibrium, initial minus change, or plus change actually. We substitute in our Ka expression, we have for acetic acid, the value of Ka is 1.8 times 10 to the minus 5, right? And then we just plug that in here. We simplify once again, assuming that the change in concentration is very small compared to the initial concentration. We get this. We solve for X, leaving us with 0.0016 molar concentration. Once we have that concentration, because it belongs to X, that means that we have the concentration of hydronium, which means that plugging into our pH expression minus the logarithm of the concentration of hydronium, we get a pH of 2.78. That's out of the question. The other half is the percent ionization, which is going to be the value of X over 0.15, and that gives us a 1.1% ionization. Lastly, we have this problem here. We want to figure out what is the value of Ka for a given acid. We can do that, so long as we have initial concentration and something more. In our case, we're going to have pH. As you guys know, we can relate pH with concentration of hydronium through this right here. Concentration of hydronium equals 10 to the minus pH. So 10 to the minus 2.27, which is what we have right here, gives us this number. And once we have that, our life becomes much easier because it's just literally filling the blanks from our ice table. Ice tables, just like in our previous two examples, water doesn't count. Initial concentration, 0.1. I have nothing on my product side. And then for every one of my reactant that I lose, I gain one of each of my products. Leaving me with this expression here real quick. I plug this number whenever I see X, put that into my expression for Ka. Ka, again, concentration of my products over concentration of my reactants. I put that in here, giving me the value of Ka for aspirin in this case.